So good morning. Um, so the exam is scheduled for the upcoming weekend. I might change the dates. I got some complaints. Some people not want to do the exams on the weekends, so I might change it starting uh, Sunday and then ending on Monday. Still have 48 hours. So I just have to look into it. Okay, so keep that in mind. Other than that, I still haven't made the exam yet, so but it's going to be probably 3 questions regarding shear and torsion, maybe 4. They should not be that difficult. And today's lectures and Wednesday's lecture will basically discuss just problems, how to solve them, where the pitfalls are in the problems. Start off with this lecture shear, majority in half of the next lecture shear as well, and then say a half lecture on torsion. Torsion often is the easier of the two anyways. So let's see. So let's start with a problem. We have an L shape. We have height h, width a, and we have thickness d1. And we have secondary structure, same shape, but that one's basically thin walled. We still have our width a and our height h. And again, thickness is d as well. So the question is, in this case, we also have a shear force going through the cross section. So we have also somewhere a shear force. Doesn't matter where it is for now. And the question is, can we apply, or what's the effect between thin walled and thick walled? So question, what is the difference between thick and thin walled? And for now, we're just going to look at the difference or the effect on IXX, IXY, and IYY. Well, actually, we can only affect on the IXX and IYY, because if you look at this problem, we have only one shear force given. So if we sum it up, the problem SY is given. So our shear force equation would go simplify to something like this: IXX. We also know there's no symmetry, but because SX is not given, the contribution of now actually we do have to calculate IXY because it still comes in a subscript denominator. Never mind. So we have to look at the effect of these three. So what we'll do is just calculate IXX, IOY for all of them. So this is thick. And then we calculate IXX thin. And then what we're going to look at, what the percentage difference is we're going to look at, say, thick over thin. On the reverse of the thin section over the thick section. And we're going to see what that percentage difference is. Okay? So that's basically what you would do in this problem. the problem has a subsequent second part where you calculate the shear flows, but for this case, we're going to focus on only looking at the percentage difference. So I'll give you guys like 5 minutes to just start off. I'll just start off with the tick one, do the IXX tick, IYY tick, and IXY tick, and then we do together the thin weld, and we look at the percentage differences of these three. So guys, just 3 minutes at start, and then we will start. And what I will do now, for now, just start with also writing out the procedure for yourself. So what the steps are, and then we can go through them. Normally, I would give you basically 10-20 minutes to do it by yourself, and then we could go through it together. But I want to go through this a bit faster and focus on different problems as well. Okay, I'm going to assume that you guys did a procedure at least, then we go through it ourselves. So basically the procedure for this problem is pretty straightforward. So we have an asymmetrical cross section. We cannot locate the centroid immediately, so we basically have to calculate it. So step one would be it's called solution. Determine centroid. And then step two is just calculate moment of inertia for both sections. Okay, let's start with this one, tip weld. So tick. In this case, we will have again basically summation of areas with respect to a point. If we choose the bottom left corner, we will get h of minus t. That's basically this area first, multiplied by the thickness. That's the area, and then what's the contribution to with respect to the x-axis. Yeah, so with respect to the x-axis will be here in the middle. The thickness is t, so it's basically multiplied by t over 2. Plus this part is basically at, it's the area, and multiplied by a over 2. And that's the distance from its centroid towards our center point here. At least this left axis, where we calculate the x-axis from, okay? And we divide that by the total area, of course. And that's area from the first part was h minus t multiplied by t plus a times t. Give us some numbers that we can actually get some calculations with. So we are going to assume our numbers. Let me see, 3, 4, and 1. So a is 3 centimeters, h is 4 centimeters, and t is 1 millimeter. So this is 30, 40, and 1. So if you do this correctly, what we get is you plug in the numbers and you get 6.8 millimeters. We repeat the same for the thickness, the thick weld, and then y. So we know the denominator basically remains the same. It's h minus t multiplied by t plus at. And the numerator will be h minus t multiplied by t. That's again the area. And now we can look at the location with respect to the centroid. And that will be this section, which is h minus t over 2 plus the thickness. So multiplied by h minus t over 2 plus t. plus t. And then we're looking at this part. That will be AT. And then from the y-axis, again, we're looking at this as our location, reference point, so that's distance is t over 2. So that will be AT multiplied by t over 2. And then we do this correctly. Let's pull this up a bit. 6.8 millimeter. And if we do this correctly, we get 11.8. And now we do the same for the thin wall. And the benefit is, if we write it out basically symbolically, if we apply the thin wall assumption, we can just see which terms basically disappear. So let's do x thin. And that case is basically we assume there's no difference. So this t over 2 basically drops out. So this whole term or this section basically drops out because you assume they coincide with each other. So you assume that the y-axis basically coincides with the vertical flange. So in this case, you only get AT multiplied by A over 2 divided by HT plus AT. And if you do that correctly, you get 6.43. And then y thin. Again, we're going to assume that these axes basically correspond or coincide with the axis of our reference point. So if you look at that, we get HT multiplied by H over 2. And then if you would do this one, it will be AT, but then this axis corresponds with your reference point, so there's no distance that you travel to. Okay? So that one basically becomes 0. And then HT plus AT, and that one is equal to 11.43 millimeters. So we already see there's a small difference, and next point is to see how that difference affects our moment of inertia. So I'm gonna erase this so I can continue working on load the figures. Let's call this X bar, Y bar. This was 6.43. This was 11.43, and here we have X bar was 6.8 and Y bar was 11.8. That's reference.
What was the equation for y thin again?
Sorry?
What was the equation for y thin again?
So for y thin, what we have is, so basically you're looking at with respect to this axis, right? Or with respect to that point. So you know there's always the summation of area multiplied with the distance towards your reference point. Let's call that A curly bar over the summation of the areas. And then for x, you basically substitute x. So reference to the y-axis. Then we get is, if we look at the bottom, that's always easy. That's the summation of areas. That's basically h times t plus a times t. And then for a thin wall, so if you look at a local coordinate system, this is what we have here, right? So we're going to look at
HT times H over 2, right?
yeah. And then this one, because the coordinate basically coincides, basically 0. So this you get HT multiplied by H over 2. And then for the thick wall, we had this section as well, but that one basically just drops out. Because this location and so the height with respect, if we zoom out for this one, we had our reference point here, and this was our local centroid. So the distance between our say, horizontal flange, width flange, and this reference point here at the bottom left, that will be T over 2. But in the case of a thin weld, you assume it's basically 0 thickness, so these two coincide. And therefore, this arm that you normally have is basically 0, and that drops out. So let's look at the IXX. So we know we still have basically the equation that we apply is the 1 over 12 h cubed t plus our Steiner term. And the Steiner term will be important because now our centroid does not correspond to any of the reference or local centroids. So we can plug it in. So let's start with the bottom. So we get 1 over 12 multiplied by, so in this case, this is HB for the width. So the thickness is T, so T over cubed. The width is B, plus its corresponding Steiner term. And that will be the area, which is AT, multiplied by the reference shift and reference axis. So in this case, that will be y thick, or centroid, minus T over 2 squared. And now we can do the same for the top one. That's plus 1 over 12. We get h cubed T plus ht multiplied by y bar sorry, I made a small mistake. So this becomes h minus t cubed multiplied by t. Because we still have to, we calculated our centroidal axis with respect to this point. So we still have to take that into account. So in this case, the total h is makes sense. You have a question?
In the first equation, it's T cubed B or A?
That's A, sorry. Yeah. So, sorry, this makes sense. So this h to the bottom. So that's the reason we do h minus t cubed multiplied by t. Okay. And then we add the Steiner term to it as well. So the area is h minus t multiplied by t. And then its Steiner term, that will basically be y thick. So that will be, let me see. Yeah, h minus t over 2 plus t minus y thick, and then squared. So you have your traditional 1 over 12 h cubed b terms, those two here. And then for each section, you have a Steiner term because it's a thick wall section. And then if you plug in the numbers, let me see, get 117284 millimeters squared. And then we can do the same thing for the thin weld. This for a second. IXX. And if you do always the thick weld first, you can basically ignore which terms disappear if it was a thin weld assumption. So in this case, the 1/12, this t cubed would disappear, so you only have to deal with this standard term, and of course you ignore also the local thickness. So this becomes AT multiplied by y10 squared plus that's the straight section. So that will be 1/12 h cubed t, and its local standard term, that will be plus ht, that's its local, that's the area for this section, and then the standard term would be h/2 minus y10 squared. And if you do this, you get 12,190.5 millimeter. So now we can basically look at the differences. So we said we're going to do Ixx of thick versus I of thin. So that's what we do. So for Ixx, we get this, sorry, we said we do thin over thick. Thin over thick. So we get 12,190.5 over 11,728.4. Yeah. So if you do this, you get 103%. 103, and multiply by 100 to get a percentage. So basically 3.9% difference. So we're going to repeat the same thing for the moment of inertia and yy. So let's do that as well. Iy. So we get basically then the t and a terms flips. So you get a 1/12 t a cubed, and the standard terms goes basically towards x. So you get at a/2 minus x bar. I'm just going to type in x bar and y bar plus 1/12 t to the power of 3. So h minus t to the power of 3 plus ht multiplied by t multiplied by ht over 2. So it becomes x bar minus t over 2 squared. And if you do this, plug in these numbers, let me see, we get 55,818.4 millimeters to the power 4. Similarly, we can do it for here. So we get Iyy, it's 1/12 Ta cubed, and then plus At, and then A/2 minus x thin squared plus this t. Here we get t over t cubed, so that disappears. Only have to deal with this section. So we get ht and then x bar squared. If you do this, you get 6107.1 millimeter. Then we can do the same thing for Iyy. We get 6107 over 5818. And we get that's 104.9%. Still below the 5%. And then we can calculate the moment of inertia of Ix bar or Ixy. So in this case, that's equal to the area multiplied by xi by I. In this case, the area in this case for AT, that's AT, and then you get see A over 2 minus x bar two yeah that's correct plus h minus t multiplied by t multiplied oh sorry this is multiplied by y bar, and that was y tick minus t over 2. Yeah. And then plus h minus t multiplied by t, and then we multiply by minus x bar h over t over 2 plus area x minus t over 2 multiplied by let me see h minus t over 2 plus t minus y. And on this side, I don't know these numbers by the way. Let me see. Well, at least I don't have the thin wall number, the thick wall number. X, y. If we do this for the same thing, what we get is AT multiplied by A over 2 multiplied by A over 2 minus X bar minus Y bar, or multiplied by minus Y bar, plus HT multiplied by minus X bar multiplied by H over 2 minus Y bar. And this one, I do have a number, it's minus 5042.9 millimeter to the power 4. For some reason, I don't have the Y bar calculated. But I think the difference lays in between these two numbers. So the conclusion still remains the same. I think in the lecture I say often it's within 5%, you can ignore it. Basically that percentage, it's always up to the engineer to decide what percentage it is. Most of the time, if we say it's below 5, between 0 and 10%, we can ignore it. Definitely below 5, we can ignore it. So in this case, you can make the justification saying it's below 5%, therefore I ignore it. But if you, as an engineer, decide it's my marker, I'm going to set it at 1%, therefore it's higher than 1%, therefore I can continue calculating the shear flows using thick wall, still would be a valid solution. But in this case, I would always go for the fact if you can ignore it, because it just makes your life simpler. And then you can go and calculate the shear flow problem. In this case, the equation would reduce as well, because now we have only Sy given. So we basically have to deal with Sy, Ixy, over Ixx Iyy minus Ixy squared, and then the integral from 0 to s of Tx ds minus sy Ixx Iyy, then Ixx Iyy minus Ixy squared, 0 to s ty ds. And the only thing that differs is it will be a bit easier to calculate the y and the x and your moment of inertia. You just don't have to deal with the thickness part of it. But regardless, both of them give you the valid solution. The idea is to realize that this is basically a simplified version of the equation. So normally, what I would do if you get such a problem, actually start off with this equation, apply all the assumptions. Say, for example, if this was symmetric, then you could already argue that Ixy is not needed, and therefore make your life one step easier. Because Ixy will be 0 anyways. So it doesn't matter whether, there's maybe a percentage difference in the two values between thick and thin, but because in the equations you don't need it, it's no need to calculate it. And you also don't care what the percentage is. Even if that mirror some way, somehow will be 10,000 times larger and no longer needed, it doesn't matter because you're not going to use it. Because it will be 0. Okay. So this for that. So basically in this problem, the question was basically focusing on moment of inertias. I think that's always a key point of any problems, is to be able to identify the moment of inertias and calculate both for thick walled and thin walled. And you will have to calculate moment of inertias, which is simple as that. You cannot go, you cannot avoid it. So for the second problem, we're going to basically do some shear flow calculations. And we're going to see let's pick out which one are we going to do. Okay, there's a comparison section problem. I think that will be nice. So we have two cross sections again, but both of them are thin walled. The flanges are A in length, and the height is H. So one of them is a C section, and the other one is a C cross section. Again, we have A and height H. So question is, we have a shear force Sy X through the shear center. Which is better? Which is better? So in this case, the question is which of the two cross sections will perform better given in shear. So what we have to focus on is we have to calculate our shear flows. So calculate shear flows, QSs, and determine max QS. Okay. Now we have a couple of numbers given as well. So H is 40, A is 20, T is 2 millimeters. And we can assume thin walled. So again, we have to calculate the centroids first, and we can know this one has at least one axis of symmetry, so this one is relatively easy. So in this case, we still have to calculate the centroid, the X bar location, and and this one, you actually don't have to calculate, you can justify it by looking at it. So how do you justify by this one looking at it? Say, imagine splitting it up in 3 components, right? Splitting it up in 3 components. So the centroid of the center one, lies in the middle. That one's straightforward, right? So now imagine what this part does. So this centroid, local centroid, also is in the middle of its own local axis. So if this was your cross section, you can say the general, your general centroid will be, due to this top flange, will be shifted up and a bit to the left, because that's where basically the mass area centroid is located, right? So this flange is similar to that flange. So the contribution of this lifting it up and shifting it to the left is basically contracted by the bottom flange by pulling it down and shifting it to the right. So the centroid will lie in the middle. And just by just looking at it, you can do the calculation and you will come out with the same conclusion, hopefully. So, but just to save yourself on time, you can justify that and just say x bar. Say, assume this is my coordinate system, x, y. So going from the bottom, x bar would be 0, y bar would be 20. For this one, we know it's lays somewhere at y bar is 20. So y bar is 20 by definition, because we have symmetry. And now we calculate the center of the x bar. So in this case, it will be, again, summation of areas over, say, ai xi over summation of areas. So in this case, summation of areas, I always start off with that. So that's 2at plus ht. And the top one will be, so this one will be 0, so you only have to determine the top parts. So you will get a over 2, yeah, so you get basically so the area, that's a times t multiplied by a over 2, a over 2, and top one is the same, so you can just multiply this by 2. So what we get here is the 2's drops, the t drop was the bottom t's, so we get a squared over a plus, c, sorry, 2a plus h. Yeah, this drops, divided by t there, so the t drops and 2at. And that should be 5 millimeters. That's correct. So we get 400 divided by 40 plus 40 is 80, is 5 millimeters. Yes.
Oh, so if you're not specifying in the question, if we should assume a thin wall, should we calculate and find out the difference?
No.
Again?
You can assume, if it's not specifically mentioned, it's either thick wall or thin wall. I think based on you, first of all, if it's drawn like this, always assume thin wall. If it's drawn like a thick bar, I'll probably specifically mention to you that it's a thick wall versus thin wall, then you have to calculate it. But if I don't mention it, I think you're safe to assume that it's a thin wall. And if it's, as long as you state it, as the problem, the origin of the problem lies with me, and you will not get penalized for it. Say, if I want to calculate thick wall, but I don't specify specifically thick wall, and I give you a drawing like this instead of like a very clearly defined thick wall, drawing like that, then I think the problem lies with me. And then if you still do the calculation saying I assume thin wall, therefore I x, y, y, then you will not be penalized in any manner. So we calculate these two. So we know this is 5 millimeters. 5, and based on symmetry, this is 20. And then we just calculate the same thing. We calculate IXX, IYY, and IXY for the Z section, because in this case we need all three. So keep in mind, even though I use basically the axis symmetry cross section to determine that the centroid lies in the middle, that doesn't mean that IXY is equal to 0. So you still have to calculate IXY because there's another symmetric cross section. Because this is symmetric cross section, we basically can get away with just calculating IXX. And the reason again is, if you look at the shear flow equation, we have Q, say QC. What we get is SY over IXX, 0 to S, TY ds. And QZ, what we get is IXY, SY, IXX, IYY, IXY squared minus SY, IYY, XX, IYY minus IXY squared, 0 to S, TY ds. And here we have an integral from 0 to S, dx ds. So again, start off with the equation, then calculate, then determine which moment of inertia is necessary. So if we would just start off with by looking at the problem and calculating IXX, IYY, and IXY for the C section as well, then you realize you don't need it in your problem. You just wasted some time. So again, for this take-home exam, it doesn't matter. For 48 hours is plenty. You should be able to solve it. I will aim for like 1 or 2 hours, so you get plenty of time. But on the exam, like if you have an in-class exam, these small things add up, can take up a lot of time that you are wasting for no reason. Okay, so let's calculate the moment of inertia for the Z section. We calculate IXX first. And we know that these two are basically symmetric, or like these two are same length. So we're going to use that to our advantage. We can calculate AT. And we also know that this doesn't have any contribution in only has the standard term contribution. So AT times YZ, Y bar squared plus 1 over 12 H cubed T. This one coincides with the centroid, so that doesn't matter. And then we get 42666.7. And YY, we get in the YY case, this basically doesn't have any contribution. These two have, so we can use again the factor 2. So there'll be 1/12 T times A cubed plus the standard term. That will be AT A over 2 squared. Yep. And that will be 10,666.67. And then the moment of inertia around IXY. So again, let's write that formula out as well as AI, XI, YI, summation of it. So let's do, in this case, we know that basically the centroid of this vertical flange will coincide with the centroid of the cross section that will drop out. 1 second. So we know that this contribution is 0, so we have these two contributions. And now we can notice that these two basically don't cancel each other out. And the reason is the area might be the same, so we have AT. So if you now look at XI, basically with this location, for say, let's take the top one first. So X is negative, Y is positive. So we get minus A over 2 multiplied by, say, H over 2 in this case, or Y bar. So let's call that Y bar. Plus, we get this part, that's again AT. And in this case, the Y bar location is negative and the X bar location is a positive. So we get A over 2 multiplied by minus Y bar. So now you have negative multiplied by positive is negative number plus negative plus positive, so this is a negative number. So there's basically they don't cancel each other out. This Y bar is basically H over 2, by the way. So if you plug this in, we get negative 1600 millimeter to the power 4. Yes?
So in the IYY, there won't be a third term for the vertical part?
No, because the vertical coincides with this local coordinate system. The local coordinate system corresponds with the centroidal axis of this cross section.
But that just eliminates the standard term, not the BHQ.
So by now it's thin wall. So in this case, for the IYY for this section, that would be 1/12 T cubed H.
So T cubed is
Yes, thin wall. So because that one disappears for the thin wall section, and the standard terms is HT multiplied by 0, because the coordinate systems.
So we could just ignore all the terms that are squared and higher.
Yeah, because you have thin wall. So that's what we started off with. Like we assume it's a thin wall section, so we automatically ignore anything. We use the thin wall assumption, so we ignore if D is equal or greater than T squared. And this section, the moment of inertia, IXX only, so makes our lives a bit easier. Let's see. So we have our central located here. So we get 1 over 12. Yeah. So we get 1 over 12 H cubed T plus the two standard terms. That's AT plus or multiplied by the distance towards this axis. So that will be, in this case, 5 millimeters. No, sorry, distance towards the Y distance. So in this case, it will be 20 millimeters. So that's Y bar squared. And if you do that correctly, you get 42,666.67 millimeters to the power 4. So let's do, I'll basically type this out as well and post it online later today, definitely before the exam, but let's see how far we can get. So we have now our moment of inertias, and the question was which one's better, so we have to calculate our shear flows and determine where our maximum shear flow lies. So next step is calculating these two for identifying the coordinate system that we're going to use. 1, 2, 3, 4. 1, 2, 3, 4. And calculating all the shear flow sections. And again, based on the based on the geometries, we can assume that these two are equal on opposite side. These two are equal on opposite sides, so we can also ignore one of the calculation steps. We also know that the shear flow is maximum when at the centroid, so we probably want to evaluate. First of all, we want to come up with the equation for 2, 3, and then evaluate at the centroidal axis. So once we did this, we go basically into the calculation step for the shear flows. I think we did this already one time before, so let's focus on the Z section first. QZ. And we're going to use 1, 2, 3, 4 as coordinate systems. And we start at point 1 or point 4 because we know our start shear flow at that location is 0. So let's do segment 1, 2. What do we know about that? So we have to come up with x-axis and y-axis coordinate system. So we know that the coordinate system for y remains constant. So y will be h over 2 minus h over 2, to be exact. And the x in that equation there, we will start at x is a, and we will go to x is 0. So we get this a minus s plus the equation. And to be 100% correct, s1, because this is segment 1, segment 2, segment 3. Again, this is often what goes wrong here. It's not a trivial problem. So if this is unclear, let me know. I can go in more depth. And we just plug in our equations. So we get Q 1, 2 for the Z section, and we get Sy Ixx, y minus Ixy squared, 0 to S, and then we set T times, well, let's T times X ds, and then plus, but it becomes minus, so we get minus Sy Iyy Ixx y Ixy squared, and then we get 0 to S ty ds. Okay, so let's first look at the integration bounds. So segment 1, we go from 0 to a. So let's fill that in. So the 0 to s becomes 0 to a. The x and y were already defined earlier, so let's fill that in as well. So this becomes a minus s1 ds1, and this becomes minus h over 2 ds1. So if we basically do the integral of this, we get as minus s over 1, s1 over 2 squared. And here we get just h over 2 minus h over 2 squared. So let's do the integral as well. So this, if we do the integral, what we get is t times as1 minus s1 squared over 2. And here we said this becomes t and h over 2 s1. And here we have a minus 1, minus h over 2. So I'm just going to put this to a plus and discard this minus. So this will be our equation for the shear flow in segment 1, 2. And before we can calculate segment 2, 3, we have to evaluate at point 2. So what we say is that the shear flow at point 2, so Q2 is equal to Q1, 2, evaluated at S is equal to A. So we plug in S is equal to A, so 20 millimeters. We have all these numbers given, SY is still unknown, so we can calculate where that value will be, and that will be equal to 0.0107 SY. So now we know what our shear flow at point 2 is, and we can use that as a starting value to calculate shear flow of 2, 3. So I'm going to keep this here. We're going to go to segment 2, 3. And let's again identify what our basically X and Y coordinate system in segment 2, 3 is going to be like. So we know our X coordinate system is 0, because this corresponds with our axis system. So that's easy, 0. And our Y coordinate system, it will go from minus h over 2 to plus h over 2. So we're definitely starting at minus h over 2. And we're traveling a total length of h. So that's plus s2. And if you would plug in the bounds, if I plug in s2 is equal to 0, we get out minus h over 2. And if I plug in my upper bound, h, I get h over 2, minus h over 2 plus h. So I get plus h over 2, which corresponds to this coordinate here. So this must be my y definition of y. And since we did this, we can also immediately see that here we had our txds, x is 0, so this part of the equation would technically drop. So again, for Q1, Q2, 3, you have this part was the integral of txds, so that one drops. So you get minus sy ix yy, or iyy, ixx iyy minus ixy squared. And then the integral from 0 to s ty ds, and you cannot forget to add q2 to it. So plus q2, because that's our starting point value there. So okay, let's do some substitution. So first of all, let's start with the bound. We travel from point 2 to point 3, so we travel from 0 to h. So we get 0 to h, that's our bound. We identified t remains, and we identified that y is h over 2 plus s2 ds2. So that's our equation, and y q2, that's what we calculated here. So that is plus 0.0107 sy. So this is our equation. And now we do the integral. So you get minus sy ixx iyy iyy ixx iyy xy squared. And this becomes, of course, t h over 2 multiplied by s2 plus s2 squared over 2 plus 0.0107 sy. And then what we can do for the, technically you can basically stop here for the equation, for the question, because now you can evaluate that. Let me see at central location and be done with it. But if you want to draw the full shear flow distribution, you want to calculate Q3 as well. So let's do for completion. Q3 is equal to Q23 evaluated at S is equal to H. So if you plug in H, you will see that you will still get the same value, 0.0107 SY. And it makes sense because even though it's not symmetric, the shear flow, how the shear flow flows is symmetric. The cross section might not be symmetric, but the shear flow, the flow of the shear is symmetric. Okay. And if you want to continue, say for 3, 4, I'll just give you the X and Y location. So the Y location will be constant. That will be say Y will be H over 2, and X would be going from 0 to minus A. So you get basically that one is equal to minus S1 or yes, S1, S2, S3. So if you want to do that also, that will be the correct values. And here, what we had earlier, this was equal to A minus S1. Now we just have equal to minus S3. Again, if you fill in your first coordinate, S3, which will be X is 0, correspond to this side. And if you fill in X is minus A, you get your location 0.4. Okay. And then the thing is, like I said, for the maximum shear flow, what we know is locates at the centroidal axis. So what we can do is, instead of calculating Q.3 at S is equal to H, for max, what we do is Q max, Z, that will be equal to Q23 at S equal to H over 2. And you can fill in that number. And you get this 0.0321 SY. And that's the reason why I said basically you don't have to calculate Q3, it's just for to be complete. But the problem does not specifically ask for it. So you could have stopped at this point and then say the maximum corresponds with our centroidal axis, so at H over 2 at segment 2, 3, how we calculated it. So you fill in H over 2 and that will be sufficient for this problem. Okay, let's quickly calculate. Yeah, I can do that. So let's do for the C section. That's slightly easier. So SY, IXX, 0 to S, TY, TS. That's our Q, C. So we can start at Q1, 1, 2. So what we get is minus SY, IXX. And then we get 0. I'm going to go through this a bit faster, not overshoot the time. So that bound is 0 to A. T, Y remains a constant, so minus H over 2. ds, so we get this SY, the minuses cancel, IXX. And then what we get is multiplied by T, H over 2, S1. So if you want to have QC 0.2, we evaluate Q12 at S is equal to A. And if we do that correctly, see that one. Yeah, let's do it here. We get 0.01875 SY. Then QC 23, we get Q2 minus SY IXX, then 0 to H, that's our bond, T, and then Y varies from minus H over 2 to H over 2. So we get minus H over 2 plus S2 TS ds S2. So if we evaluate this, we get 0.01875 SY minus SY IXX. So what we get is evaluate that integral. So this, yeah, okay. So we get T, and then we get minus H over 2 S 2 plus S2 squared over 2 and then you can evaluate at let's evaluate just at C is equal to H over 2, so we go for QC max. So this is Q23 of C evaluated S is equal to H over 2. And if you do that correctly, we get 0.0281 SY. So let's compare those two maximum values. So here we have and here we have like I said, I will type this out and post online as well. So, what do we know? Let's see if we have correctly. 8.03. Yep. Okay, so what we see is that to answer the question, which one is better? QC max is less than QZ max. So therefore, you can argue that for the same shear force, you get less stresses or less maximum shear flow in C, which is directly correlated because the thicknesses are equal. Keep that in mind. So if the thicknesses were different, then you basically also have to calculate tau C max and tau Z max. Okay? Because to get the shear stress, you multiply by the shear flow, multiply by thickness. But in this case, you assume that same thicknesses. So you can say that for the same amount of shear force, that's why the shear flow QC, Q, and C is less than in Z. Therefore, the C section is more efficient in handling the shear force. So it will require more shear force before it can potentially hit the maximum failure stress levels. Okay. Are there any questions? So we did two problems. I hope to do another problem on shear on what's that? When? Thursday. And then I'll post all the solutions online. We do one problem on torsion. Like I said, torsion is very straightforward. Very, I think it's the simplest of all the three problems, especially with because it gives you a constant shear flow. You just have to basically memorize two equations. That's T is 2 times AQ and rate of twist equation. And then in the weekend / Monday, you will have the exam. Like I said earlier, I postponed by 1 day, so it probably starts on Sunday, ends on Tuesday morning then. Okay, thank you very much. See you guys on Thursday.